Alright, in our next session, let's review what we covered in the last lecture, which was mainly about altitude measurement, right? So today, we will consider another very important parameter, which is speed measurement. How do we measure the airspeed of our aircraft? And what is the principle behind it? This is related to Bernoulli's principle. So, specifically, let's take a look. Today, we mainly want to introduce these three main topics. First, we will introduce the basics of pipe flow and Bernoulli's principle. Before introducing the specific knowledge, I would like everyone to first observe an experimental phenomenon. Let's take a look. This is a Venturi tube experiment. Let's look at its specific process. Nanjing. Look, this is a glass bowl. The sides are wide and the middle is narrow. Then there is a U-shaped tube connected to the narrow part and the wide part. We can see that when using an air pump to blow air towards one side, the colored liquid in the U-shaped tube rises and moves. When the valve is closed, it is level. So the above is an experiment with the Venturi tube. Why do we always observe this phenomenon in the experiment? This is due to the Bernoulli's principle that we are about to introduce. Before we delve into the specifics of Bernoulli's principle, we need to discuss the foundation of Bernoulli's principle. What is that? It is the conservation of mass and the continuity equation. Let's assume we have a one-dimensional pipe, a tube, which has a varying diameter, as we can see, as it flows from upstream to it has. The cross-section here is 1 square meter, half a square meter, and 1 square meter. Based on our everyday common sense, let's assume it is a normal flow. What is meant by steady flow? It refers to a flow that has stabilized over time. At this point, what should the flow rate, the mass flow rate, be like at each cross-section? It should be consistent. Why is that? We can consider a counterexample. If the mass flow rate changes, and the mass flow rate through a unit cross-sectional area changes, what would happen? If there is a place where it continuously accumulates, then it will definitely become blocked, right? Or if it decreases, what does that indicate? It means there is a breach and it has leaked out. Therefore, for this pipeline, it can only be considered a steady, one-dimensional flow if the flow rate and mass flow rate are consistent at all times. With this relationship established, we can understand that for each cross-section, we can formulate an equation. At each cross-section, the cross-sectional area A multiplied by the corresponding velocity VA, and then by its density should be calculated. The product of these three should be a constant value, which means the mass flow rate remains unchanged. Now, why so? Why do we use V here? We can assume a very short period of time, such a brief moment. And during this short moment, we can consider that the distance traveled is very short. At this time, in fact, the cross-sectional area hasn't had the chance to change. So, this is a very short segment. In this case, its area is A, and the distance from here to here should be delta T multiplied by V, which gives us its volume, right? Then, multiply by R, and you can cancel out the terms here. So ultimately, you can obtain the result. A conservation relationship, which is the continuity of mass flow rate, if we further consider the fluid flowing in this pipe, and if its density is constant, for example, like the water we mentioned in the previous lecture, right? Its density is constant. Or for air, a low-speed airflow can also be approximately considered as having constant density. In this case, we can further cancel out the density term, allowing us to obtain each. Its velocity, multiplied by the cross-sectional area, remains constant. Now, if we assume that the flow velocity at the first cross-section is 52 meters per second, then what should be the flow velocity at the second cross-section? Since V multiplied by A is conserved, right? In this case, if the area is halved, the velocity should double, correct? Therefore, for the second cross-section and the third cross-section, we can respectively determine their velocities. This is the continuity equation, and in fact, we can observe many instances of this continuity equation in everyday life. For example, if you go to our Zhuiyuan Road campus, on a particularly windy day, you can observe this at the entrance of the new main building. If you stand there, you'll feel a strong wind flow. Why is that? Because this is a large wind tunnel, and the surrounding area is quite large. But when it reaches the entrance, the area becomes much smaller. According to the continuity equation, where the cross-sectional area is smaller, the flow velocity is faster. Additionally, for instance, as we learned in middle school about rivers, we know that generally, in places where the riverbed is wider, the flow velocity is slower, and in narrower places, the flow velocity is faster, right? Also, when we were kids, we might have played with a water hose. If we wanted to spray the water further, we would pinch the opening to make it smaller. This is also because, for a normal flow, the same principle applies. It is a matter of mass conservation, and it follows the continuity equation. So when we reduce the cross-sectional area, the flow velocity can increase, allowing it to spray further. This is an example of how the continuity equation manifests in our daily lives. With the continuity equation as a foundation, we can now discuss what Bernoulli's principle is all about. Here, we will briefly derive Bernoulli's principle for everyone. During this derivation process, I would like students to focus on it's important to understand under what conditions Bernoulli's principle is applicable, as it has certain prerequisites and cannot be used in every situation. Please pay special attention to this. When deriving Bernoulli's principle, we will use a basic scenario of a one-dimensional pipeline. Here, we can see that the whole pipeline is of a fixed length. Note that it is of a fixed length, and it involves incompressible flow. Initially, we focus on this segment, which we have marked in green, and it spans from X to Y. At the node X, the area is A1, and it corresponds to a height of H1. Then, when it flows to the section at Y, its cross-sectional area changes to AR, and the corresponding height changes to HR. At the two sections, the speeds are V1 and, at the latter section, V2. All right? Next, after a very short moment, at time t, this entire green segment of liquid will flow to the right, correct? Let's simply illustrate it. And this is the situation. The original section at X has moved to the section at X1 prime. The Y section has moved to the section at Y1 prime. So, in this case, we want to find the relationship between the pressure and speed at these two sections. So, how do we determine this? We still use the basic assumption of the continuity theorem mentioned earlier, which is that we assume this time is very short, an especially brief moment. Therefore, during this flow process, we consider that. From the X section to the X1 section, and from the Y section to the Y1 section, during this process, because the distance is very short, the cross-sectional area does not have time to change. Therefore, we consider this segment to be an equal value segment, and the latter segment is also an equal value segment. Since the area does not change, based on the continuity we discussed earlier, we also mentioned that its speed does not have time to change either. we consider the speed to be v1 in the range from x to x and in the range from y to y. All are vr. So let's further examine this. During such a brief period, the section at x flows forward a distance that should be its speed, v1 multiplied by this small time interval. Similarly, at the outer interface, the forward flowing distance is the speed of the flow, which is v2 multiplied by. In this flow process, we need to focus on assuming that it is an energy conservation process, meaning that there is neither friction nor heat exchange occurring. We need to focus on how a certain quantity changes. So what are the factors in this motion process? Forces will do work. What forces are acting on this? Can we see them? What forces might be present in a flowing liquid? Someone mentioned that there should be pressure in the liquid, right? When you dive to a certain depth in water, you can feel the pressure, like the pressure on your ears, right? So, as it flows, it has pressure. And at the same time, it is affected by gravity, correct? So, throughout the entire process, one of the forces doing work is pressure, and the other is, it's gravity. Hey. All right, so how does pressure do work? Let's see. The entire segment flows from xy to xy, right? So on this surface, there will be pressure doing work, correct? Similarly, on this surface, there will also be pressure, which acts as resistance to its movement. In this way, we can represent it. Later, we can directly write it out as an equation. Then, when analyzing, we can also make a simplified consideration. Although the flow goes from xy to xyi, there is a part that remains completely unchanged throughout the entire flow process. That is the segment from point x to y in the middle, because it is a normal flow. It hasn't changed at all. Therefore, we can simplify it by considering that the entire flow process is essentially just moving the segment xx directly to the location of yy. This makes our analysis much simpler. In this way, we can consider that during the flow process, there is a situation where pressure does work, and another where gravity does work, converting the kinetic and potential energy of this part into the kinetic and potential energy of the segment on the right. All right? That's our analysis of this process. Next, let's express it mathematically. First, let's take the fluid segment xy as the object of study. So, how does pressure do work? It should involve the pressure on the left segment. What should the work done by B be? How did we calculate positive work in the first lecture? B multiplied by what? B multiplied by displacement, right? So we should be doing positive work, and the increase in work should be force, which is pressure, multiplied by area, correct? How far does the positive work go? It should be this segment at point xxx, right? So it should be v1 multiplied by. Similarly, on the right side, this pressure does negative work, right? Because under its influence, the direction of displacement is opposite. So the work done should decrease energy. However, it should be P2 multiplied by this AR, correct? This is the force. And then multiplied by the distance, which is VR times T. Since it is negative work, there is a negative sign in front. All right, so this is the work done by the internal pressure. Next, let's take a look at how the kinetic energy changes. We just mentioned earlier that its kinetic energy actually changes from the kinetic energy of this section to the kinetic energy of that section, right? So its kinetic energy should first be, in the final situation, 1/2 of m2v2, which represents the kinetic energy of this section. Then subtract the initial kinetic energy of this part, which is 1/2 of m1v1 squared. Here, m represents. In this way, we can write it out completely. It should equal the original volume multiplied by the density, right? Okay, so this m2 should correspond to area A2 multiplied by A2 delta G, its length, right? Then multiply by the previous R, density. The latter part is similar, and we can write it out completely. Next, we will consider the change in potential energy. Yes, we say it also changes from this segment to that segment. So the total change in potential energy should be m2 multiplied by gravitational acceleration, then multiplied by the height minus the initial m1 gh1. Similarly, we will express m1 and m2 separately using the previous method. Finally, there is another relationship that we can use, which is the continuity theorem. We say that there is the continuity theorem and the incompressible relationship. First of all, we have this in the entire cross-section. Monday multiplied by A1 multiplied by A1 is equal to R multiplied by V2 and then multiplied by A2. When the fluid is considered to be an incompressible fluid, we can cancel the two axes so that it becomes the final form on the right, so that it is at each cross-section. Multiplied by the area is equal. All right, by listing the above equations, we can simplify them. First, we have the relationship of energy conservation, where we say the work done by energy includes one part where pressure does work, right? And another part is gravity, where gravity does work. So, what kind of changes does this result in? The main point is that its kinetic energy has changed, right? All right, in this case, let's take a look. Then we have this A, which is the work done by the pressure, should be equal to the change in kinetic energy plus a change in potential energy. Then we have this 1/2 RHO A2 V2 squared minus 1/2 RHO A1 V1 squared, which represents the change in kinetic energy plus the change in potential energy should equal the work done by the pressure. So here we can write it out. And then, from the continuity equation we mentioned earlier, we know that the product of A and V is equal. So we can cancel it out throughout this equation. This way, we arrive at the following expression, which gives us the Bernoulli's principle we need. Since we are primarily concerned with the situation at each cross-section, we keep the conditions at each cross-section on one side of the equation. As for the other side, moving the second interface to the other side gives us the final expression in this form. So what do we see at one cross-section? It should have 1/2 RHO V1 squared. Then, adding the gravitational potential energy rho at this cross-section, plus this part of the pressure, P1 equals 1/2 V2 squared plus H2 plus P2. This is what we refer to as Bernoulli's principle. Now, let's recall what assumptions we used in this process. This is very important for us when we analyze its applicability later. So let's review. What basic assumptions did we make? All right, time's up. What assumptions did we make? We have 4 assumptions, right? So within this, it affects the applicability of our national effort law. To summarize the law, during our derivation process earlier, we can actually see that it is essentially an energy conservation relationship for flow within a pipeline. Its applicable conditions are, in fact, firstly, we say it is a one-dimensional normal pipeline flow, right? Because at that time, we used the continuity theorem, didn't we? Therefore, it must be a normal pipeline flow. Additionally, since we say it is an energy conservation relationship, whenever we use an energy conservation relationship, we say it requires no friction and no heat exchange. Thus, it should be non-viscous, because only with viscosity does friction occur. So non-viscous means there is no energy loss due to friction. At the same time, it should be particularly thermal, that is, a flow without energy exchange with the external environment. And finally, we say that when we use the continuity equation, we cancel out the mass term, because we assume it is an incompressible fluid. And for an incompressible fluid, its density is the same at all positions. X. So, what kind of fluid satisfies incompressibility? One example is a liquid, and another is air under conditions of free flow at relatively low speeds, which we can also consider as an incompressible fluid. This is one of the conditions under which Bernoulli's principle applies. All right, here we need to emphasize that for a fluid that is non-viscous, adiabatic, and incompressible, we can refer to it as an ideal fluid. So, what is an ideal fluid? It is a very simplified concept designed to facilitate our description of it. The above applies to a general fluid, for which we use or apply the laws of motion. However, for pilots and aircraft designers, we are more concerned with air rather than water. Compared to water, air has its own characteristics. One particularly notable aspect of air is that its density is very low. In the flow of air, the change in altitude is also very small. Therefore, when studying air, we usually disregard the gravitational potential energy because its range of variation is too small. As a result, in airflow, the commonly used equation of motion is simplified to this form, which applies to a flowing conduit. So, how do we handle it? Record the relationship between its speed and pressure at different cross-sections of the conduit. At each node, the pressure plus half the product of the square of the speed and the density is conserved along the entire conduit. This is the equation of motion we use in the process of airflow. In this context, we usually assign a name to each term in Bernoulli's equation. The first term, this pressure value, we refer to it as or static pressure. Now note that this static pressure is slightly different from the static pressure we discussed in the atmospheric system in the previous lecture. When discussing Bernoulli's principle, what does this static pressure refer to? It refers to if we place a pressure gauge at this position, or more precisely, a pressure sensor here, then this gauge can directly provide a reading. And this reading is what we refer to as static pressure. And the latter part, 2 times the velocity squared, actually represents the kinetic energy of the fluid. However, for convenience, we refer to it as dynamic pressure. Thus, Bernoulli's principle can be described as stating that at every cross-section of the fluid, the sum of static pressure and dynamic pressure is conserved. So, with conservation, what is the final pressure we obtain? We refer to it as total pressure. This is how Bernoulli's principle is expressed in terms of static pressure, dynamic pressure, and total pressure. Here, we need to emphasize an important concept regarding static pressure and dynamic pressure. Static pressure is the reading obtained directly from a pressure gauge. However, dynamic pressure is actually a conceptual construct and cannot be directly measured with a pressure gauge. All right, let's assume we have a flow tube. If we completely block the rightmost end, what would the speed at that point become? Once it becomes zero, what should the static pressure at that location be? After zero. We say that the sum of static pressure and dynamic pressure equals the total pressure, which remains conserved throughout the flow tube, right? So, if the flow reaches the end and is blocked, what happens to the speed at that point? It becomes zero, right? Okay, once it becomes zero here, what about its dynamic pressure, right? It becomes zero, doesn't it? At this point, its pressure should be the total pressure, correct? So, if I place a pressure gauge at this blocked position, its reading should be the total pressure, right? This is a basic concept because of the relationship between dynamic and static pressure changes in the pipeline. With this principle of fluctuation, we are interested in what functions it can serve. And we would like to invite everyone to first watch this short video. So this is an experimental situation in a smoke wind tunnel. It uses many smoke-emitting pipes upstream of the tumor body, which continuously expel smoke. By using this smoke, we can observe certain phenomena. Alright, from this smoke wind tunnel, if I don't look at this middle section, because this section is not a steady flow, right? It changes over time, so we mainly focus on these outer parts. Now, these outer parts are actually a steady flow. By using the smoke and observing its changes, we can understand the conditions within the entire flow field. So within this, the entire trajectory that the smoke follows, if it is a steady flow, then the entire path it takes is called a streamline. For a steady flow, the streamline and the path line are the same. Through this analysis, we can directly obtain the pressure and velocity distribution within the entire flow field from the streamline and path line. Why can we directly analyze and obtain such a situation? In fact, we need to use Bernoulli's principle. The first assumption of Bernoulli's principle, as we mentioned earlier, is a one-dimensional steady flow, which is clearly a pipe flow. So why can we use it here to analyze problems in open space? Next, we will focus on explaining this. First, let's look at the flow situation within a closed pipe. For the flow of water through a search theory, use an asterisk to indicate fluid units, allowing us to focus on their movement. We see that in such a closed pipe, if we generate these small hydrogen bubbles, by observing these hydrogen bubbles, we can understand how the flow is throughout the entire pipe and how its speed should change. Then, intuitively, we can see how the flow rate is at this position. It should be faster, right? Similarly, according to the continuity theorem we mentioned earlier, we also know that in wide places, its flow rate will be slower. In narrower areas, the flow rate will be faster. Now, with the volatility law we just analyzed earlier, we also know about kinetic energy and pressure energy, right? In the entire flow tube, they have a conservation relationship, correct? So can we further understand how the pressure changes at these two positions? In the wider area, the pressure should be relatively larger,
right? In narrower areas, the flow rate is fast, so the pressure will be relatively lower. This describes the continuous flow situation within the pipeline. So how do we relate the flow in a pipeline to the flow in our three-dimensional space? Earlier, we used smoke. And if it's a steady flow, the path the smoke takes actually forms a series of streamlines. For a steady flow, the streamlines and path lines coincide. Now, if there are small dust particles in the air, these dust particles will glide along. A streamline like this. Now, for the area between these two streamlines, if we consider it, we can actually equate it to the flow in a pipeline. Why? What should be the direction of the flow velocity on the boundary of the pipeline? It should flow completely along the pipeline, right? Will there be flow in this direction? No? Why not? Yes. He was trapped on the spot and couldn't leave, right? Well, for the flow between the two streamlines in space, we also analyze the position of the streamline. The speed of each place is actually the tangent direction of the streamline. If it's all in the tangent direction, then there will be a velocity perpendicular to this tangent direction. I wouldn't have it either, right? So, for the air, the region enclosed between two streamlines is actually completely equivalent to this pipe, isn't it? Air cannot exit from the boundary of this streamline. So from this, whether it's between two streamlines or in three-dimensional space, it's formed by countless streamlines enclosing this. We call it a stream tube. This stream tube is actually exactly the same as the flow in a closed pipe. Previously, we derived a certain flow rate in a pipe flow. And in fact, we can use it here to express the relationship between pressure and velocity changes along a stream tube from upstream to downstream. By observing the expansion and contraction of streamlines, or the expansion and contraction of the stream tube, similarly, we can understand how the velocity behaves in the wider sections of the stream tube. The velocity will be relatively low, and the pressure will be higher in the narrower sections. The velocity is relatively high. The pressure is relatively low. In this way, using the concept of a stream tube, we directly apply the closed one-dimensional pipeline flow derived earlier to the entire open space. Thus, we can use it to analyze the dynamic characteristics of systems we are interested in, such as airplanes and other objects. In many of our practical work processes, we use various methods to understand the distribution of streamlines throughout the entire space. So here, we have drawn the streamlines of some typical objects. The flow situation formed by the combination of many streamlines is what we call a streamline map, or sometimes a flow map, etc. By observing the changes in the distribution of streamlines as mentioned earlier, we can actually understand the entire flow field during the flow process. What are its pressure and velocity distributions like? Well, at a great distance, its velocity should be the same everywhere. And its pressure should also be the same, right? Because it's far from the object. It hasn't been disturbed yet. So everything is the same at this point. However, as it gets closer to the object, we can see that the shape of the streamlines changes. And where the streamlines narrow, there will be an increase in speed. The pressure, on the other hand, will decrease. Conversely, after flowing past the object, we see the streamlines disperse, which means that the pressure should increase and the flow speed decrease. This is some of the information we can observe using a streamline diagram. Here, we have provided typical streamline diagrams around an easy-to-handle object, as well as vertical and inclined flat plates and a sphere. In line with situations in our daily life, we can actually simply sketch out its general trend, and later we can conduct a more detailed analysis of it. This is a basic application of Bernoulli's principle. Next, Let's take a look at how we can apply the principles of motion in specific engineering problems. The first application I want to show you is the experiment we demonstrated at the very beginning, which is the Bernoulli's ball experiment. This experiment is also known as the Bernoulli's ball, pressure gauge, and flow meter experiment. So, it is a device used to measure flow rate, converting the flow rate into pressure for measurement. The U-shaped tube in this setup is essentially a pressure measuring device. We read the height difference between the two ends, and based on what we learned in high school, we should know that this height difference corresponds to the pressure difference between these two ends. The pressure difference, or the pressure differential, right? So, how do we use this kind of device to measure flow rate with a Venturi tube? Let's take a simple look. First of all, we say that within this Venturi tube, it satisfies the Bernoulli's equation. At this point, at the first node, its pressure plus kinetic energy should equal the sum of the pressure and kinetic energy at the second section, right? So at this point, because we have placed such a U-shaped tube, we can actually calculate the pressure difference between the two sides, right? From the height difference between the two U-shaped tubes, we can directly determine what the pressure difference is. Therefore, we leave the pressure difference on one side of the equation, and on the other side is the difference in dynamic pressure between the two ends. Now, what about the difference in dynamic pressure? This includes density, and there's another one. It's the velocity term. So the velocity term. At this point, we are concerned with the flow rate, right? The flow rate is actually related to velocity. So let's see how we can further express the entire flow rate through the pipe. As mentioned earlier, for the U-shaped tube, we have the pressure difference on both sides should equal the A density of the liquid inside the tube multiplied by gravitational acceleration, and then multiplied by the height difference. As for velocity, the velocities at the two previous points, we actually have a relationship derived earlier under steady flow conditions, which is the conservation of flow rate. For an incompressible fluid, in the case of low-speed flow supply, we can cancel out the density term. Therefore, at two cross-sections, its flow rate is equal. So we have A1 multiplied by V1 equals V2 multiplied by A2. At this point, if we make a change, we can express the velocity at the second cross-section using the area difference between the cross-sections multiplied by the velocity at the first cross-section. From this, we obtain three equations, and after organizing these three equations, we can ultimately derive an expression for the flow velocity at either the first or second cross-section. So, what is the main advantage of using this method to measure flow rate? Generally speaking, in engineering, there are two types of devices for measuring flow velocity and flow rate. The first type is this one, a device that records flow velocity and flow rate through fluid impacting a turbine. So, what problem does this have? A portion of the fluid's kinetic energy is converted into rotational energy, right? This results in energy loss. In contrast, if we measure the flow rate from a pressure measurement perspective here, then this part of the loss is eliminated, right? That's the first advantage. The second advantage is related to something that rotates. It experiences wear and tear, right? Over time. It will break down. But in this case, are there any moving parts? No, there are absolutely no moving parts, right? This way, its lifespan is significantly extended. Therefore, in our large industrial sectors, in fact, many use this type of Venturi flow meter. Its biggest advantage is that there is no wear and tear. Moreover, it directly converts the measurement of flow speed into a measurement of pressure. This is a very important application of Bernoulli's principle. And this is in the industrial field. Next, let's talk about another very important area, which is the banking sector. When each of us goes to flight school, the first planes we fly, they should all be piston propeller planes, right? So, in piston propeller planes, there is a very important component on the engine called the carburetor. The carburetor works like this. Its main function is to atomize the fuel while taking in air. It creates a mixture of fuel and air, which is then fed into the engine. The carburetor itself is essentially a Venturi tube. Let's take a look at it. If its air intake is open facing downward, then as the air enters from below, we can see it narrows, right? The narrowed part is called the throat. And when it goes from a larger opening to a smaller one, what happens to the flow speed? The flow speed increases here, right? And then what happens to the pressure? The pressure will drop. So there will be a very noticeable effect around this throat area. Since the pressure is the lowest at this point, the oil sprayed out will quickly atomize in this area. After a while, it mixes with the incoming air to form a relatively uniform mixture. Then, finally, it flows downstream into the combustion chamber of our engine. This is the basic working principle of our carburetor. So what about this carburetor? Essentially, we say it's a Venturi tube, and it follows certain conventions when in operation. At the position where the flow speed is low and the pressure is strong in the throat, the flow speed is high and the pressure is low. In actual flight, due to this pressure change, and considering the actual weather, the carburetor might encounter a common issue, which is carburetor icing. Let's review what we discussed in the previous lecture about the ideal gas law. We said pressure and the temperature. Assuming we are dealing with a gas of constant density, as the pressure changes, its temperature will also change accordingly. If the pressure decreases, the temperature will. If the density remains constant, what happens to the temperature? It will decrease along with it, right? Now, if you assume that on a day when you are flying, the weather is quite humid, and the temperature is already close to the dew point, then at this time, if air flows in through the intake, then when it flows to the throat, the speed increases. And if the density decreases, as the speed increases, and the pressure decreases, then we say, according to the complete state equation we mentioned earlier, due to the pressure decrease, what happens to the temperature? It will also decrease. Due to the very humid weather, at this time, the relative humidity in the air is already close to 100%. So, if the temperature drops further and falls below the dew point, what will happen? At this moment, the water in the air will precipitate out. When the precipitation becomes severe and the temperature drops further, this water will turn into ice. And this ice will directly form around the throat area. Now think about it. The throat area is already the part with the smallest diameter, and if this part freezes over, then it could potentially cause a blockage of the entire throat if the throat becomes completely blocked. The engine will stall, right? Then Therefore, in fact, before each flight, we need to check the weather forecast. We need to understand the temperature and humidity conditions of the day. If we find that the weather is prone to icing, meaning the temperature is relatively low and the humidity is high, we need to constantly prevent this ice formation during the flight. What do we do about icing? We use a very important device, which is the carburetor heating system. It actually extracts some of the engine's heat to warm the carburetor and melt the ice in the throat area. All right, let's take a short break.